Hello, everyone. We're going to be starting. That's very nice. Hello. We're going to be starting our very first speakers session this morning now. Okay? We have some of the preeminent representatives from the biggest and most important companies, including the European Space Agency. Forgive me, I keep repeating that. Going to be up on stage here speaking. And after they all speak, they will be getting together again, all five of them, to talk more in depth with a moderator leading them. Our very first speaker is from Thales Alenia. He is the physical design manager and has been involved with aerospace engineering for over 25 years. Ladies and gentlemen, please welcome to the stage, Ángel Martínez. Gracias.
Okay. Para pasar es aquí. Okay. Good morning, good afternoon, let's say. My name is Ángel Martínez, as my colleague has presented me. My duty in Thales Alenia Space, mainly with what we do in our company, in our site in Madrid, in Spain, is the payload equipment, electronics for the satellites. So now I'm the technical manager of physical design, which is perform the thinking of the engineers to the real world. That's our job. And mechanical and electronics. So, but now, today, I'm representing Thales Alenia on the group of RD, Research and Development, in Thales Alenia Space. So Florence Montedron is the person who leads us or coordinates all the group, all the efforts around the world in Thales, and put all together to benefit inside the group and outside sometimes. So my presentation this afternoon will be devoted to this R&D department or group. Okay. Okay. What we're going to do today? Today we are talking about the AIM process. All of you already know the physics, the techniques we use for many of the processes in additive manufacturing. We are going to show you a little heritage we got in Thales Alenia Space, mainly with a space problem, with space solutions and materials, etc. There are many differences. We don't know any machine or any other hardware. Sometimes we will do, but not now. And we rely on the manufacturers. And what we do mainly is to standardize and give some coherence in this type of techniques. Okay? So afterwards, just pointing what is our motivation in the space sector and what we are focused on in this R&D group in Thales, and the typical validation we use to have enough rely on the hardware we do, because in space, as you know, it's very hard to go up there and fix something broken. So we need to know with some certain level of reliability on the materials, on the processes, etc. And this is what I want to share with you today. Those ways, procedures, etc. To be sure to have some, let's say, confidence on the hardware we need to get outside in flight. Okay. So, okay. I don't know if you can read. Yeah, you can read very well. So you know additive manufacturing is layer manufacturing, it's layer by layer. We use in 2 different materials. It's metallic, LBM, which is laser beam metallic melting, and SLS, which is for polymers. The difference are the power of the laser, whatever parameters, I don't know. But this is the main material in space we use up to now. There will be another, we are running another researching, and, but this moment, this is what we can do. And the benefits we get in space is the optimization of the hardware. This is the main point for us. And we optimize the hardware in 2 ways, mainly, with up to now, in my knowledge, is to optimize mechanical parts with the strength, forces, etc., and thermal optimization. These 2 main issues has been shared on the industry in our point of view. Okay, so this is one example of the optimized organic shape probably you see everywhere in the space sector at least. Okay, we go to different materials mainly used, 3. Aluminum we use for structural, mainly because their possibilities to manufacturing. I mean, the manufacturers know very well which are the parameters to manufacture that materials, and this is the benefit for us because there's some mastering on this material. Titanium, because the ratio, mass and strength is a very good thing, but not very good conductors, and polymers that we use for not main structural parts, just for piping, tubing, etc. And all of this we externalize. We don't manufacture ourselves. Okay, so this is 2 good examples I will say for the International Space Station. It's a toolbox. This toolbox has been manufactured in, I don't know if it says Ultem. You probably know this material, and it's very good, I think, in mechanical behavior. And another one is some tubing, what are already in orbit, and very good repetitivity, which is very important for us, of course. Model has been very well correlated with the mathematical model we designed in the very beginning, and now we know all the different parameters to tune that mathematical model and finding elements to the real world. Okay. And the repetitivity has been little by little, not at the beginning, I have to say, very good. So right now, we can be sure that the first piece on the series will be almost or reasonably the same as the last one on 10th or something like that. They're little series, I mean, let's say. Okay, so what is important in this toolbox or any other hardware is that you can perform one hardware, this toolbox, and when the need of the toolbox changes on fly, you can easily change the design with a parametric software, design software, and change it and send it to the International Space Station and manufacture it on fly. So you don't need to get up the specific hardware or piece. And this is one experiment we have finished last year in the space station. We flown a printer, and we did the first part made by Alenia, Altran. There is one collaboration with, let's say, and the investigation and research of Italy. I don't remember right now the name. But all this collaboration make one thing possible. That printer, we we put that printer on the space, and we are able now to print those different shapes on this International Space Station. Okay. This is our heritage on flight. We will say that at the very beginning, we have put in flight many brackets. Mainly, this is brackets on aluminum, the heritage on aluminum. We put in many satellites, let's say Turkmenistan, MonacoSat, Telcom 3, KoreaSat, many of them. Some of them in flight, and some of them will be on flight. What is interesting, what happened with this historical. We started with this bracket here, and this is the qualification program. This is the first thing we did to understand what happened with this kind of manufacturing. The first one we did, we put one structure original and get into the computer, and we optimized that bracket. And the result was too much revolutionary. We see some organic, you probably see very organic shapes, etc. And at the beginning, we didn't believe on this shape because it was too much for engineering brain. So we did, okay, we're gonna do something similar, but with our engineering brains, put in all the shapes, analytic shapes, shapes that we feel comfortable with, brackets and reinforcement. And we did that with additive manufacturing. And we save about 20% of the weight, which is very important for the space sector. Okay, and we did the test, and the test was enough, good, but not really amazing or surprising. And afterwards, we believe on the computer, did the optimization, and we arrived at 50% of mass saving with the same mechanical behavior. That was very amazing for us, because at the very beginning we started to not believe on the mathematical models coming from ancient formulas. And with it we rebuilt again this bracket, and we found that the computer really makes it work. It's very incredible because some of the structure they got some incredible shapes that are very hard to believe on this on their mechanical results. And that's what we learned. The lesson learned of this is just let the computer, if you have tuned very good your mathematical model, you're gonna have a very good results on that. Okay. This is the titanium. Titanium we use for equipment that have not enough or need heat transfer, and we need rely on the strength, okay, on the force they hold. So, and we got more than 80 flight parts and 50 different references already in orbit. So let's say we can say that we got enough experience with the space sector to go one step further right now, a more complex structure. But this is the status right now. There are another research and development programs that will not be here, but in the future probably get much more challenging results. Okay. Challenging. This is a group. Just to point out our commitment with this technique, just to explain how we work in Thales Alenia Space. We got a group centralized in Cannes. Florence Montredon, I don't know if the pointer here, this girl here, is our manager, let's say. She's coordinating all the different sites of Thales in the world to put in common all experience and get better benefits of the additive manufacturing. And this is our focal points for each type of technology or country, etc. And we perform meetings every two per year to get in common, put in common all the information we got and experience. It is very, very good experience and very tight group and collaborative. I'm really proud of it. And ESA, we work with ESA in all of the standardization, let's say, and documentation to let the people share our experience and put in common all the standard document, all materials, etc., to be used in the space sector or other industries. So this is something that we get inside our souls, let's say. Okay. We got just passing through our validation philosophies. There are two of them. This is the document the issue will be on ESA in the coming months, I think. Is the way you can proceed to get a validator or qualified an additive manufacturing bracket for space sector. There's a way, mainly is taking the vision of the machine, additive manufacturing machine. You can tune it, get the parameters, and check with different probes the machine, and get that ready to manufacture in series. The other way is look at the piece, look at the bracket with a part, and then make the same thing by testing each piece. So it's high cost, I think. It's going to be better, I think, in the future. But these two ways are different, and you need to know about the program, what you're going to do your satellite. If your satellite is an observation satellite, let's say, is looking at Mars or whatever, and you got only one sensor, etc., you might see the piece. You might check the piece, do all the testing, computer tomography, whatever, to be sure that that piece is going to be functional on Mars. But on the other side, you probably need a satellite constellation with communication, and you need thousands of pieces, and you cannot test every one of them. So what you're going to do is the other way, is you make a global test the machine, and with a certain amount of probes, you can check those and then let the machine work with certain repetitivity. So this is what I would document with what we are doing with ESA, and this is the two different philosophies. So for series articles or acceptance with unit articles. And this is the way, the typical distribution of the samples to check that all the manufacturing has been properly done, and at the end you can rely on those pieces after some tests on the piece. And the other is check the machine, make enough samples, etc., in all direction, and test it, get the parameters on that machine, and make the series. All of this is inside a document of ESA. This document will lead you, anyone on space, interested in the space sector, to get your machine or your process ready to put your pieces, I'm talking with the manufacturers, on the space. Okay, so this is the same thing. What we do is witness samples, looking at the piece, fatigue and shear samples, computer tomography scan, 100% of the piece, look in the porosity, and with a certain levels on the document that you can accept or you can not accept. So this is go or not go. And functional tests, at least on the first part. Okay? Yeah. So I used to stop here the presentation just to let you know what is the procedure on the space sector, and I made a reflection in Madrid, in Cannes. We had a special experience I want to share to you. That is the amazing capability of this technology to be democratized. Let's say now in our department, what I've found is the ideas to use this technology doesn't come from the manufacturer. Sometimes yes, come from each company. So what we did is try, and was a very amazing experience, is to share this technology. You know, you can let the people know about this technology in a few hours. You can tell, you can do this optimization, you can use this machine, and with this model you can perform yourself, you can machine this. And this you can do in days with somebody that haven't any other experience before. That's you can do. So we did that. We shared this technology with other departments, even with commercial, even with financial. It was amazing. And we present the possibilities. And we did some introduction courses for manufacturing chain, for technologies, for other departments in the company. And the amazing response was many of the problems we had and we didn't have enough time to solve, they came back to us to give us the solution. Sometimes the solution was not the correct, but you empower the people to use the technology, and the results coming to you are thousands. And many of the people you never know came with 20 new ideas, having in mind that they are very approached to the technology. We got 2 printers. This is plastics. All of these pieces, we perform also brainstorming. All of these pieces, we bought about 2,000 euros, etc. And right now, the cost of these tools for mounting, etc., is about €1. And also the time on the manufacturing line is about 1 day or 2 days. So what I want really share to you is empower your company, each of the department, to get the people who use this technology. All of this department knows now how to make a design with open source design software, perform the optimization, and build it themselves. And those departments come to my department to print their solutions. And this is what I share with you today. Thank you very much all. Thanks to Thales.